Well, thank you very much, Sonia, for the introduction and for putting together the wonderful workshop. It's a pleasure to be here and tell you about this recent work that I did in collaboration with Kunrum, who's in the audience, and Irene. So I think after the previous talk was absolutely amazing injection of information. I learned a lot from the talk. It was very fast paced. So after that, I think it's maybe good to step things down a little bit. So it's going to be a Blackboard talk. Like the nice thing about Blackboard talk is that you're forced to have a slower pace. Well, hopefully that leads to for more room for questions. Okay, so please engage in ask questions as much as you possibly can. Okay. Well, so indeed, this is the title is what can we do about neutrinos and B-L in dark dimension scenario. So the dark dimension scenario, you heard a little bit about it yesterday, is this a scenario inspired by Swampland. So the dark dimension is a little bit like large extra dimension scenario. So it's similar to large extra dimensions, as we heard yesterday in George's talk. But while in ordinary large extra dimension scenario, you try to tie the size of the extra dimensions to the electroweak hierarchy problem. So essentially, you put gravity at the TeV scale. In that dimension, instead, the size of the extra dimensions is correlated to the size of the vacuum energy. Okay, so that leads to a different range of parameters, but it's very similar. And of course, you know, it's a nice scenario because it leads to experimental signatures. So one of the experimental signatures, right, is that it leads to the size of the extra dimension is the idea is that in the dark dimension there is one extra dimension, which is between 1 and 10 micrometers. Okay, so just to put reference, in the current experimental bounds are at 30 micrometers. So it's not too far off from that. So that's interesting for detection. And you heard yesterday in George's talk that it can be you can give a nice cosmological history, a nice cosmic history. So you can fit the DESI data, etc. It's interesting. So there are many things you can do with dark dimension, but at least in the way that we originally presented the scenario, there are some things that. So there's also like connections to neutrinos. You can put neutrinos in the extra dimension, which is what we'll talk about. But the way we did it originally, there's a very nice feature of the standard model that we just didn't discuss in the scenario, and that's B-L. Okay, so B-L, variant number minus lepton number, is an exact symmetry of the standard model. It's is conserved by every standard model interaction, and it's a very special symmetry because if you add right-handed neutrinos, which as we were hearing in the previous talk, maybe that's a good thing to do, then it's a symmetry that is anomaly-free. Okay, so that's something that is quite special about B-L. So what that means is that this is anomaly-free, and you know anomalies are. For the purpose of this talk, obstructions to having a gauge symmetry. The fact that B-L is anomaly-free means that you can gauge it in the standard model, and it's a consistent thing to do. So it's sort of like a bit of an appealing feature of the other dimension scenario that we were not talking so much about what happens to B-L and what is gauge. So that's what we'll try to do in this talk. Okay. So I will start with a little bit. You already heard about review of dark dimension from George's yesterday. So I will start a little bit on the same story. Oh, there's another thing that I should mention that is interesting, but maybe not quite explained from point of view of dark dimension. Okay. Whenever you're trying to build a model of particle physics that connects to vacuum energy and extra dimensions, there are several coincidences that you might want to explain. And here's one that to me is very mind-boggling. It might just be a coincidence, but I sort of want to take it seriously, which is that the scale of the vacuum energy is within 1 order of magnitude to the neutrino mass scale. Okay? So these are two things that in principle have nothing to do with each other, but they are, they just coincide there within a factor of 3 from each other. And while we tried to give a bit of an explanation for this in the original dark dimension scenario, the whole story was not quite satisfying. To me, this was one of the original motivations of dark dimension, try to connect these two things. And so what we will see in this talk is how by coupling B minus L to the dark dimension scenario, you can actually get to a model that explains to this more or less in a natural way. Okay. So let me start with a review of dark dimension. So the idea of dark dimension scenario, it starts with an observation, if you want, or about the string landscape, which has been codified in the form of conjectures. So for instance, there we were hearing from Georges yesterday about the anti-de Sitter conjecture, distance conjecture, or the emergent string conjecture. But what it boils down to is that whenever you have small parameters like really small parameters in string theory, okay? In every example that we've studied so far, an arbitrarily small parameter means that you're in a corner of string theory where one or more extra dimensions are decompactified. Okay? So when you do string theory, string theory is time-dimensional, you have this internal manifold. So what is the size of these extra dimensions? They could be very small. They could be up to the string scale or the Planck scale. But in most cases where you have, in the regions where the effective field theory that you get from that has very small parameters, there are corners where the theory looks like some non-compact space times some internal space whose size R is much bigger than, let's say, the string scale or the Planck scale. Okay? So what does that mean? Yes. Yep.
I think the statement that I feel like there's strong evidence for is that if you have sort of a limit in which you can make parameters be small, or like a sequence of activa that are getting increasingly small, that this is true. But we have strong reason to think that there can't just be accidental cancellation somewhere where some parameter is small or in the interior moduli space just for no good reason.
No, I cannot exclude this. I'll get actually this is going to come up in a bit more quantitative way in a couple of minutes. But no, I would say that this is, so certainly there's, for as you know very well, for some observables, there's very precise statements about this. Like, for instance, like the distance conjecture when a gauge coupling becomes very small, there's a one parameter family of vacua, as you're saying, then you're in this kind of situation. I cannot rule out that there are compactifications where accidental cancellations happen and they don't satisfy these patterns. What I would guess, and this is a guess, okay, it could be wrong, but I would guess that these are not typical. So what I would guess is that the typical, based on what we've explored so far, I would say that, for instance, the typical string theory vacuum, if it has let's say it's not supersymmetric, it has a non-zero vacuum energy, I would say that vacuum energy is typical vacuum has of order Planck or M strings, like some high energy vacuum, right? Out of the vacua that have small vacuum energy, I would say that the typical ones, at least the ones that I know how to construct, satisfy this property. That could be fine-tuned. I'll get back to that in a moment. Yes, Lisa?
Just a related question. I mean, we know in ADS, for example, one extra dimension, that the cosmological constant is from cancellation. So you could have large cosmological constant in bulk, large cosmological constant in brain, and you can have any KK mass you want. Because it doesn't really matter what brain is as long as the tuning is done, so that the Israel junction condition is satisfied.
So from effective theory, from models that you can write down, that is absolutely true. When I go and look, for instance, the ADS vacua I can get in string theory, they satisfy the scalings that I'm going to tell you here.
Well, what about the constructions that we used to do KKLT, where you have?
Good. So KKLT is a little bit like what Matt was saying. So in the KKLT, there's some cancellations, and you gotta have some cancellations to have the small vacuum energy. And for instance, the people, the group of Liam and friends, they actually find these calculations, these cancellations. And certainly you could, in principle, try to look for even more cancellations, so to avoid the scaling that I'm gonna tell you now. But if you don't do that, KKLT vacua satisfy the scaling of dark dimension. This was in a paper of Blumenhagen and friends. Let me get back to that, because the two questions are related is gonna be just in a second, really, because what I was going with is, okay, I have some large extra dimension. What does that mean? Well, that means that I get to use higher dimensional effective field theory to compute the vacuum energy. So the vacuum energy is gonna come from some scalar potential, and the scalar potential is going to have a bunch of ingredients that are going to depend on my theory. It's going to have some fluxes or some branes or some Gaugino condenses, whereas there's going to be a bunch of terms, okay, that they're going to be very dependent on the solution. But if I am breaking supersymmetry, okay, and I have this tower of Kaluza-Klein modes that you get from string theory, from just like having large internal manifold, then these Kaluza-Klein modes, they're going to contribute to the scalar potential simply by the usual one-loop diagram. You have a one-loop particle of mass m. You have a particle of mass m put in a one-loop diagram, contributes to the vacuum energy. So there's going to be one contribution here. Let's say the one loop. And very generally, you can compute this just by summing the contribution of the whole tower of particles. And if you have a manifold of size r, then this is going to be 1 over r to the fourth, simply by dimensional analysis, if this is the vacuum energy of a 4-dimensional compactification. Okay? So the statement of that dimension is just saying, well, okay, imagine that there is no fine-tuned cancellation between this guy and the rest of the other guys. Okay? It can still be that the whole thing is small, okay? Because each term is small. And in fact, we have concrete compactifications where that happens. But if you assume that there's no cancellation between these two things, then immediately this tells you that R has to be greater than or equal to b to the 1/4. Okay? So that's the scaling of dark dimension. So in some sense, I would say this is something that happens in a generic vacuum, which has this property. You can certainly imagine fine-tuning this away, but that's an independent fine-tuning from the fine-tuning you need to do to get the vacuum energy small, at least in a large class of models where you can explore things concretely. Okay? Oh, well, so you could imagine maybe, so I definitely need to get one fine-tuning from point of view string theory to get connect with observations, which is the vacuum energy is small. So I'm not looking at generic vacuum, I'm looking at a vacuum which has a small vacuum energy. That's a fine-tuning I have to do just to match the observations. And you could imagine, well, could it be that the same fine-tuning that makes V small sort of like fine-tunes this with this other thing? Okay. That is not what happens, for instance, in, well, for instance, there's in vacua where you have this thing contributing as a general, as an important ingredient to the solution. It cannot happen, like in vacua with Casimir energies. Also in KKLT, it doesn't happen. So this V1 loop is a correction, which is actually smaller than the free-level terms. So I'm just saying that there are examples of top-down constructions. In fact, most constructions that you do that achieve a small vacuum energy, this thing is not fine-tuned. That's all I'm saying. And indeed, this might be a statement about the constructions that I'm looking at, but yes?
And I just object to the word consistent. We don't really have consistent construction. We don't really know.
So yeah, thank you. I should have clarified what I mean by consistent construction. Okay, so I'm playing a different game here, and you might object to the game, but the game I'm doing is, can I look at string compactifications where I have a positive small vacuum energy? Maybe that's not, well, certainly not de Sitter. Maybe it's time dependent, but I can certainly look at constructions where I have a small vacuum energy and then ask what happens. That's sort of like where this is coming from.
And connected to, I think, Matt's question, usually, so the question is, if you have a standalone theory, which is not a sequence of theories which are getting there, then Matt's question applied. Like, how do you know this is a sequence of theory? So in all the ADS examples where lambda can be arbitrarily small, you have a sequence. We don't have any case in ADS where lambda can be arbitrarily small, which is not the sequence. Like, take, for example, ADS 5 times S5 kind of stories. or n equals to 40 angles, you can have exceptional things like E8 or E7. There's no, there's no infinite sequence of those. But whenever you want to get lambda sufficiently small, the only examples we know is a part of the sequence. That's certainly true for negative lambda.
Because we also don't have the tools to go deep in moduli space.
I'm just saying that all the examples in string theory for negative lambda, lambda being small, is a part of the sequence.
Yeah, that's because those are the ones that are constructed.
We don't have any examples other than these. So I'm just saying those are the examples. You could say, well, that's not a good enough evidence. We can't discuss that. But all the examples we know.
But sort of by definition, if they're fine-tuned points, you're not going to find them.
So let me say differently.
Yeah.
If there are infinitely many fine-tuned points, that's against the whole principle of finiteness of active, which is motivation of the whole
But there
program.
truly aren't infinite.
Sorry?
Yeah, there truly aren't infinite.
Well, so therefore, 10 to the minus 120, which is the 10 to the 1. So you want to know what is that part of? So there's going to be a sequence of that's 10 to the 120, which gets you there. So even if you take approaches like people are trying to get to small lambda, there's always part of the sequence. Let's try this one, bigger one to get to 10 to 120. It's not just a standalone E8, which is 10 to 120. 10 to the minus 120. That doesn't happen. So it's very, even though it cannot be ruled out, I think that the idea that you can have a standalone analog of the E8, which happens to have 10 to minus 120, is a little bit tough. That's what we are. We're just basically assuming that this is part of the sequence, like the ADS cases, which have no counterexample in string theory.
Sorry,
Which
can I
is
just
like-
understand that? So you don't believe that cancellation of concepts ADS?
There's no infinite amount of fine tuning possible. Like in field theory, you can write down anything you want. But in the effective field theories that you get from quantum gravity complete theories, since you have only finite number of possibilities, you don't get these typical cancellation that hopeful cancellation that won't put them away. That's the point. So you can assume generously in that one.
To me, is more like, I mean, I think that, in principle, there could be points where there's cancellations and stuff like that, but it's an interesting thing to look what happens. If you just look at the scenarios which are more like what we can construct and see what phenomenology we can extract from those. Okay? Yes, please.
Sorry to belabor this, but like the examples that we can construct, we have supersymmetry and we can ensure cancellation to keep the vacuum energy close to the classical value, whereas in our universe we have large corrections.
Yes, this is.
So should that give me reason to think that this is not going to be a typical?
Yeah, it's certainly atypical. Well, first of all, already because it's small, it's atypical. But I agree with you. Even beyond that, it's atypical. For instance, so just to answer this, let me just advance a little bit further. So once you have this kind of thing, you have this kind of bound, you essentially are led to the scenario with just one large extra dimension. 2 extra dimensions is marginal, is a little bit out there. So I'll come to that back later in the talk. So it's 1 large extra dimensions. So then, it's either a circle or something like a segment, like an interval. So I'm just gonna draw it like a segment. And, standard model fields cannot be in the bulk, because if they were in the bulk, they would have very small gauge coupling. So you just put them in some brane. Let's maybe put it at the end of the interval. So something like the standard model brane, like you do in large extra dimensions. Okay. And then the question you're asking maps to the question, okay, this standard model brane has some tension, but it also contains electrons. So what is going on? The tension of the tension of the standard model brane would be normalized by electron loops. Electron scale is much higher than vacuum energy scale. How come that the tension of this brane is fine-tuned to be so small? Okay, that is related in this scenario to why is the vacuum energy so very small. And indeed, you will have to find some sort of brane where the tension is rarely, like is very small. In string theory, that happens. Okay, you have orientifals where at the classical level, the tension is vanishing. And we even have models where you can engineer branes where the one loop corrections to the tension vanish. So it's much more than you would expect. This is this paper by Emilian Dudas, Xuxa Parameswaran, and Marco Serra, which they did this recently. Then, of course, to get this to the standard model level of precision is more loops. Okay, it's like 20 loops or something like that. So it's harder, and I think it's a very fair question.
But actually, just a counter example to what you're saying, Tom, is the bosonic string. Or superstrings is not supersymmetry. We do know enough about those to know that even though they would get vacuum energy contributions naively from infinitely many string towers, the contribution only comes from the light stuff. It's not the heavy. So in other words, there you could have also said, well, the naive calculation of the vacuum energy will give you m to the power of, let's say, 10, if you're in 10 dimensions. And you do the calculation, and naively field theory will give you infinite sum. But modular invariant of string theory cuts it down and gives you the leading power, which is the light. So somehow the magical cancellation that is not explainable in string theory, in terms of effective field theory, is explainable in terms of the SL2Z symmetry of string theory. So the explanation is, we should not be looking for explanation in effective field theory land. That won't appear, don't look for it, but we know it works. In other words, the idea that there is the dominant light power dictates lambda is the case in string theory. Now, easy to explain in effective field theory, but we know it's true.
I think what you're referring to is true at the tree level in string theory. The one loop is controlled by the tower of string states, right? So it's m string to the fourth.
But m string, it doesn't go like there's a tower of string states are reliable up to 1/g string.
Right.
They would have contributed the huge
You mean the
amount.
heaviest states don't
Heavy
contribute?
states
Right?
don't contribute. It's only
Just
dictated
like
by M
Casimir
string.
energies like this and
Exactly.
heaviest states don't
Islamic
contribute.
species
Yeah.
dominates it. So the light power always dominates.
Okay, so anyway, the picture is you have this extra dimension with the standard model brains being there, and then, you know, every standard model field lives there. And essentially the only probe of physics at the standard model brain that is not the standard model brain that you can add is neutrinos. So for instance, you could certainly add neutrinos in the standard model brain and give them a mass. That's not a scenario where you have anything very interesting to say. What you can do also is to add some 5D bulk neutrinos. So 5D bulk Dirac fermion, where the mass is 0. Okay. So if you add such a thing, so let me just write for you. So it would be like you would have like the Lagrangian would be the integration of the, you know, over the standard model brain of the standard model Lagrangian. In the bulk, you would have gravity. And a kinetic term for the 5D fermion, all right? Where, you know, I'm just putting one 5D fermion for simplicity, but in principle, to give masses to all three flavors of neutrinos, you would need to have 3 flavors of right-handed neutrinos. Yes?
Sorry, did you say earlier that you don't want to have gauge fields in the bulk because the coupling would be too small?
I haven't put any gauge fields in the bulk. I'm just putting the neutrino.
Covariant derivative on the
That's just the covariant derivative coupled to the metric.
metric.
Yeah, has to be different for invariant theory, so has to couple to the metric. If you want, I will just, yeah, okay.
What's the justification for setting the mouse?
Yeah, that's a very good question. So in 4 dimensions, you could have a fermion with zero mass protected by chirality. 5 dimensions, that's not the case. Okay, so here, this is a fine tuning. I could maybe justify it by saying adding more bells and whistles to the scenario. I could say that, you know, maybe the theory in the bulk local Lagrangian is supersymmetric, in which case you can have
Supersymmetric, you could write down the vector.
if it's in a hyper, if it's for instance if it's for instance a hyper multiplet,
Right.
then no.
Well, because you're breaking it on the boundaries anyway, Jenny.
Yeah, I am going to. Well, I mean, if the bulk Lagrangian is n equals to 2, then the bulk interactions have to be restricted to be n equals to 2, and then indeed that can be broken by boundary terms, which I'm gonna.
But you could still have a mass.
No, I don't think so. You have a hyper multiplet, is massless is protected with n equals 2. Well, 5D n equals 1. Yeah.
Important to be massless for your case.
Yeah.
For the
Well, I guess you could. You could give it a small mass, but for the kind of this is sort of what I'm doing here is what we did in the original third dimension paper. So for the scales that I'm going to mention after in a moment, yes, it's gonna matter. But I'm gonna give you a better answer for that once I introduce B minus L. Once I introduce B minus L, I will have additional symmetries in the bulk that will force the guys to be massless until the B minus L symmetry is potentially broken. Okay. Good. This is just to say that you can add the neutrinos And you can add a coupling. So how does the bulk neutrino to talk to the standard model fields? Well, so you can add a coupling. Standard model fields are localized on a brane, so you have a coupling which is localized on the brane. So you have some Yukawa. Then you have the Higgs field. Okay, so you can have an interaction term like this between these two things. So this will couple the left-handed fermion doublet to the restriction of the field psi on the brane. And this is like a very natural way to couple the two. And indeed, this is an effect that is going to generate an n=1 mass, or if you were doing supersymmetry or just a mass term. And what happens is the Higgs field gets embed, right? And the fermion psi you decompose into a tower of 4-dimensional Kaluza-Klein modes, so you use the dimensional reduction. Where x5 is just the coordinate on the extra dimension. And okay, so one 5D field becomes a whole Kaluza-Klein tower of 4-dimensional field with classical masses as usual. But then there's some mixing with the neutrino on the brane. Okay, so that gives you some mass matrix. So Concha was telling us in the previous talk how you can get how you can add as many sterile neutrinos as you want. So in this model, there's many sterile neutrinos coming from the from all the Kaluza-Klein modes of the brane.
Miguel,
Yes.
you have to specify the boundary conditions to do this Kaluza-Klein reduction.
Sorry, what?
You have to specify the boundary conditions, right? To do this Kaluza-Klein reduction.
That is true. For the time being, let's pretend I'm going to be talking about boundary conditions later. What I'm telling you right now doesn't really matter if I'm doing it in a circle or an interval. Okay, it's just this coupling. I can put the brane whatever I want, and it's just a coupling that I can write down. You see what I mean? It's a coupling I can write down. I could do this on a circle. Later on, boundary conditions will matter a bit more. So I can have this, and then effectively the mass matrix that you get looks a little bit like this. So there's some off-diagonal terms which couple to the and there's the same in the vertical, and then there's like the Kaluza-Klein masses. Okay, so there's some infinite dimensional mass matrix, and that's what you have to work with. But to give intuition for the purposes of this talk, it's much easier if I'm gonna replace this matrix by a simple 2x2 matrix, which has something like a seesaw structure. So that's gonna give you the correct mass scales for the lightest neutrino on the scale of the mass scale of the lowest sterile neutrino. So essentially, all these Kaluza-Klein modes are heavier and heavier. If you're interested just in what is the leading order properties of the mass matrix, you can replace it by a matrix which is just like this. Okay, and then you put here the mass of the lightest guy in the tower, which is 1/r. Okay, that's what I use the assumption that the bulk neutrino was massless, because I said that the lightest heavy mode has a mass of 1/r. And then if you have this model, what you can just find what is the mass of the active neutrino and the mass of the tower of sterile neutrinos, just from seesaw type formula. And so the mass of the active comes up to be this M5, by the way, that I wrote here is I put a mass scale. I need to put a mass scale here for dimensional analysis in 5 dimensions. So this is it's just a Yukawa coupling between the bulk and the brane, has some energy scale in 5 dimensions. And so what did I choose for that energy scale? Well, it's a 5D theory of gravity. The natural scale to choose is the Planck mass. Okay, there could be additional scales, but here I'm just putting it to be the blank mass, 5-dimensional blank mass. So I get this thing, okay, and then I get a tower of, the scale of a tower of stereo neutrinos is essentially controlled by this. So I get this 1 over R, which is lambda to the 1 quarter, the vacuum energy to the 1 quarter, okay? So that's what you get from here. And I told you, so this is sort of, when we wrote the first dark dimension paper, this is the model that we proposed for neutrino masses, okay? Something simple thing, we just have the neutrinos. And you know, you get the, so that's what you get. And this is not obviously the thing that I wanted to get at the beginning, because the mass of the observed coincidence is between the mass scale of the active neutrinos and the vacuum energy. So the two things don't really match. You can make them to match, okay? So for instance, we argued that, so there's some anthropic argument, which is that we sort of want the Higgs field to settle down to its BEV by now, given the history of the universe. So that puts some relation between the Higgs BEV and the potential. And then with that and a fine tuning of the Yukawa of 1 part in 1% or 0.1%, you can sort of like by hand make this thing match this thing. So it's not incompatible with the observation, but it doesn't explain it naturally. Like what comes out naturally from this is that the tower of sterile neutrinos is a tower of states whose mass starts as 1 over R, not the active one. Okay? Yes.
Is your R dynamical in this, or you just fixing it to something?
So I am, in principle, nothing I told you here depends very much on whether it's dynamical or static. In George's talk yesterday, it was a dynamical variable, and that dynamics was used to connect to the dark energy, right? So I would think of it as a dynamical thing, but it's not going to be essential for anything I'm telling you today. Okay? More questions?
Just have a question. So far, this violet is
No, nothing so far violates B minus L.
you have a 1 over R mass that it is up into. Sorry.
Well, sorry. No. Sorry. No. I mean, you're right. I mean, the moment I write this kind of coupling, I'm gonna be violating the B minus L symmetry. But in this scenario, okay, even though I explicitly break it, it's just not. It's not something that I would expect to be a good symmetry of the system anyway. It's a global symmetry, so to say.
What? I think.
Global symmetries are supposed to not be.
Associated variant, electron number to the psi right, the right hand component of the hand dimension.
Yeah, but you're putting a mass that is right. Okay, so that is
Yeah.
No, it's left right. It's left. From the standard model, it's capital left.
But this is
From the bulk, psi is the left hand. Psi is a 5-dimensional fermion. So from the 4-dimensional point of view, there's a left component and a right component. And,
So you're saying that there's a charge assignment that I can do here so that it preserves B minus L.
Before.
If you preserve it in 5 dimensions, you preserve it in 4.
Psi is you can think of it as a Dirac fermion in 4 dimensions and in the 0 mode. So it has a left component and a right component. The one that couples to the left to the lepton is the right component.
But sorry, Ignatius, maybe we can talk about this further.
The notation of that mass.
But sorry, what, Concha?
I'm not understanding the notation of it, the basis in which you are writing that mass matrix that I don't.
Oh, this is just schematic, right? Well, it's just schematic. It's just some mass matrix for to model.
Is that not a Majorana mass term?
Yeah,
The 1 over R.
Okay, that's what I'm just
The
saying.
1 over R is a Majorana mass term, and that's what's breaking the leptons.
You're saying that the 4-dimensional Majorana.
This is a Dirac.
No, but Ignatius, they're saying that when you write it like this, effectively, this is like a Majorana. There's no way to make it conservation with B minus L.
I mean, the columns are left-handed, the rows are right-handed.
This is still a direct mass.
It's a Dirac mass.
Because it's involved, it's like two of like that if I put it all in there.
It's a Dirac
the
mass.
initial way of writing it.
You should make it a 3 by 3 matrix, and the 1 over R is a Dirac
Yeah, okay.
Yeah, it's
Okay.
more refined notations needed.
I
I think he's gonna get to the part that is interesting for him. The device is gonna be key factor.
Yeah.
The way you, it's not a direct mass term, but when you couple to grab photon, there's a partner, which is the radion. Radion gets a BEP because.
The radiant gets a BEP?
Gets a BEP because it's setting the distance.
Yeah.
So it's related to the charge of the field to the ground. Like, unless those charges are all zero, you would.
You have mass terms. I didn't quite hear all of that, but
They're related to the charge under the ground.
okay. Let's. This could even be like a no supersymmetric model in the bulk. So the supersymmetry is not going to be any important.
No reason.
Then you have to write a master.
Then really you would expect a master.
Yes. So let me then go to the B minus L theory where I couldn't write a mass term. Okay. So what I really want to get to. So in this model, there's no. You can try to give global symmetry assignments, charges for the B minus L and so on and so forth, but there's no reason to do it. I mean, you expect that there's, it's a global symmetry in some sense. You expect there's no global symmetries in quantum gravity. So there's no reason to do that. So what we are going to try to do is write a model where the B minus L is gauged, okay, from the point of view of the dark dimension scenario, and see what does that bias, okay, with respect to this scenario. Okay, so what can we do to, let's say we have a scenario where gauge B minus L. Well, I'm gonna discuss this. So when we gauge B minus L, so we go back to the dark dimension, right? One thing that we can always do is we have the standard model brane. We can add the gauge field for B minus L there. Okay, so we can just put it there and be part of the usual. So that's what you usually do in any grand unified theory. So you have an SO10. For instance, if you have an SO10 GOT, then this automatically includes B minus L, and it can be spontaneously broken just by some separation of the branes here. And so you can always have it there, and that's a story that can always. There's nothing in that dimension scenario which is incompatible with that. What I'm going to be telling you about instead is what happens when instead you put the B minus L gauge field in the bulk. Okay. Okay, so when you put the B minus L field in the bulk, what that means, first of all, it's like there's some A B minus L in the bulk theory, right? And you can sort of like try to estimate what the gauge coupling for it is going to be, because this is going to have a kinetic term in 5 dimensions, which is going to be 1 over G5 squared, some integral of F wedge H star of F. Okay. And so there's some gauge coupling here. The gauge coupling has units of energy. So G5 squared, let's me just get this right. It's going to be alpha over M5, where alpha some dimension is constant. Okay. So original parameters in terms of the 5-dimensional Planck scale. So we can put it there, and well, to have a situation where when you compactify, you get a B minus L symmetry in 4 dimensions, you need to have chirality in 4 dimensions. If I reduce on a circle, I'm not going to get chirality. So I will instead compactify on an interval and put boundary conditions on the interval to see to get chiral fields. Okay. When I have boundary conditions on the interval, I need to decide what is going to happen to this B minus L gauge field. What are the boundary conditions on the interval? Okay. And there are essentially 2 possibilities. The boundary conditions for B minus L, you can either have it, so one way of encoding these boundary conditions is if you have an interval that you see as like a circle divided by Z2. So basically you take a circle and you take a quotient where x goes to minus x, where x is the circle coordinate. So that's a parity transformation. And boundary conditions, they have to do with how does the vector transform under parity. Okay? So for instance, what happens to the component along the circle? So it can transform, it can either flip a sign or not. And then the other components have the opposite parity transformation. So the case where you get the minus sign here, it's a minus sign. That means that AB minus L is a pseudo vector. And whereas the plus sign, B minus L transforms an ordinary vector. And the two give you very different degrees of freedom when you go to 4 dimensions, because for the pseudo vector, the gauge field gives you an axion field phi, while if you transform an ordinary vector, what you get is like another vector in 4 dimensions. Okay? It just comes from the dimensional reduction. So there's 2 cases that you can discuss here. We studied both cases. For the pseudo vector field, you can actually have a consistent story where you cancel anomalies for B minus L using something like a Green-Schwarz mechanism on some both topological terms. And so it's an interesting scenario where you generate neutrino masses without having right-handed neutrinos. But unfortunately, the masses that you generate are very, very small. They come from non-perturbative effects on the extra dimension. They're tiny. So when there's a consistent scenario, I'm just going to ignore it because that's not the interesting one. The more interesting one is when you do this. Okay? When you do this, there's first a very nice thing that happens for fermions. Okay? So as we were this, so I have the gauge fields, but now I will also have the 5D fermion fields that I was introducing before. And when I have this quotient, what will happen is that the 5-dimensional fermion field, this coordinate for the circle is x5. Okay, so the profile of the fermion field is x5 is going to satisfy this equation. Okay, that's just the condition that the field is invariant at this parity transformation, so that gives you a well-defined function on the interval. And if I specialize to fermion fields to the 0 mode, to the field that has no dependence on the extra circle, what is this? This is the condition that you have a chiral fermion in 4 dimensions. Okay, you start with a 5D fermion, which is Dirac, and what you get in 4 dimensions is a chiral fermion. So the 0 mode is chiral and charge under this B minus L guy. Okay. So you get a fermion 0 mode, and so you now more or less see how anomalies cancel for the B minus L symmetry. So once you reduce to 4 dimensions, what are the chiral fields that you have? Charge under B minus L. Well, there is some. So the total anomaly is going to be some anomaly from the standard model fields. Standard model fields have some anomaly in their B minus L. And if I am just adding some number of psi's, they also contribute to the anomaly because they give you Weyl modes in 4 dimensions. And so imposing the total anomaly cancels fixes how many fermion 0 modes do I have in terms of standard model fields. And the answer, of course, is that imposing anomaly cancellation, you get 3 psi's, so 3 right-handed neutrino modes. So that's interesting because in what we were doing before, where we're not thinking of B minus L as a global symmetry, it could have added 1 trillion neutrinos. Why was there only 3? So here's an answer to that. Another nice thing, which you can already see, because the fact that this thing is giving me chiral modes when I reduce in an interval must also mean that I cannot give it a master in 5 dimensions to this fermion, okay? Because, well, I mean, it shouldn't it shouldn't get a, if I was able to give it a mass term, then over another circle, we just give it massive modes. So indeed, you can actually study what happens to the mass terms you can give to these guys. So to these guys, in 5 dimensions, you could give a Dirac mass term, okay? And in 5 dimensions, that's really, if you think just about representations of the Lorentz group, that's the only mass term that you can give. But here, I need to classify mass terms also taking into account the fact that I have the gauge B minus L. So then, this mass term is different from this other thing. In terms, if you forget about the U1 charge, they're both the same mass term, they're both Dirac mass terms, but once you take into account the charge, they behave different. This is a bit like a Majorana mass term. So this violates the B minus L. So if you look at how they transform under parity, which is a exact symmetry of my theory, and B minus L, what you find is that this one preserves B minus L, but violates parity, and the other one goes the other way around. So there is no mass term I can give to my 5D fermions. So now there's a good reason why they're massless, which indeed is good. So
5D parity is important.
yes.
4D universe perspective there was
It would have to be some, it would have to be spontaneous symmetry breaking, yes. It would have to be. But in the,
more detail how that works.
well, I mean, you could imagine, well, sorry, no, I mean, okay, so the 5D theory has a parity symmetry, okay? But then I compactify on an interval. So I'm sort of like, I'm gauging it, okay? So for instance, the 4-dimensional theory I have has chiral fermions, so it doesn't have already parity symmetry, it only has CP, okay? And the CP, you would have, I think you would have to break with spontaneous symmetry breaking. Yeah. I think, yes, I think so, but I'm not sure. I think so. Okay. Good. Anyway, so you have these guys. You know, once you have this, there's another. Okay, so this is all nice, and you get the 4-dimensional frequency modes, but right now we have 2 problems. The B minus L gauge field is massless, okay? And you might think that's not too bad because even though it's massless, it's gauge coupling. So the gauge coupling of the B minus L in 4 dimensions, okay, you can just get from dimensional reduction square, this thing square, is equal to this alpha divided by M5 times R. So the 5-dimensional Planck scale times the radius of the extra dimension, which for that dimension is 10 to the 20. So the gauge coupling is 10 to the minus 10. You might think that having a massless field with a coupling which is 10 to the minus 10 for the B minus L might be okay, but actually 10 to the minus 10 is huge. The bounds that we have for massless B minus L is of order of 10 to the minus 25. So we have to give it a mass. How do we give it a mass? Well, there's a very simple way to give it a mass, even in 5 dimensions. There's nothing preventing me from introducing a charge scalar, which I'm going to do now. So I will introduce some charge scalar uppercase phi in 5D. All right. You know, I can give it a kinetic term just like this. I'm writing the kinetic term with an M5 to the front because that way, even in 5 dimensions, the scalar phi has units of energy, so it's good for units. And now this time, Rasmish, I do have a covariant derivative. So this time there really is a covariant derivative, right? So I have this guy. And then indeed, by the usual argument, if this guy gets a VEV, the mass of B minus L is just going to be, well, it's going to be G5 square root of M5 times the VEV. Okay? Yes?
Is the B minus L gauged in the whole book or just
It's this gauge field in the bulk. So it's an exact gauge symmetry. Yes, it's in the, that's why the gauge coupling is so small. So this is the formula. This is a 5D gauge field. And when you do a dimensional reaction on the circle, this is what you get for the 4D gauge coupling. Okay. So I have this guy here. And then, okay. I have a B minus L. And now that I've broken B minus L, I can give a mass to my neutrinos. In fact, I will generate a mass to my neutrinos. I no longer choose it. It's given by symmetry breaking. If you look at these things, okay, so what you can see is that even though there's no mass terms, there's a Weinberg-like operator you can write down. You can write something like this, 5 dimensions. Let me just. So there's an operator you can write down like that. And so that operator, once the scalar phi gets above, is going to give me a mass.
Psi or phi?
Sorry, what?
Is that a psi or a phi there? I think it's hard to read. Is it phi or psi?
Phi, psi.
Fine.
The other one.
The other one.
Yeah, that's just the, sorry, that's me confusing Greek letters. It's precise. So this guy can give it a mass, right? And this is not really Majorana mass. 5 minutes, yes. And well, okay, so I have the Majorana mass, and so what that gives it is it gives a bulk mass of the neutrinos, which is okay. That's just what it is. I'm just doing algebra now. And then I can go back to my 2x2 Veritoid model matrix to get the right scales. And so what I should do is I have the same things. I will just replace 1 over r here by this thing. Sorry about?
That's my run.
Yeah. Yeah. Well, you can see this like in both the.
Just want to clarify.
Yeah. Yeah.
Very good.
No, thank you. Okay. So we have this thing. And
Miguel,
yes.
parity just kills the 0. You still have all the climb modes.
Yes.
And your Kaluza climb modes are very light.
The Kaluza-Klein modes are not very light. The Kaluza-Klein modes, there's a tower of Kaluza-Klein modes that starts here. You are very right that there is a tower which is very dense. Okay? So what you have is some scale here, which is given by pi over m5, phi squared over m5, and then, yeah.
So it's still a full matrix.
It's still a full matrix. Yes. I was just going to the 2x2 because it gives you the right scales. In hindsight, maybe that was not the best presentation idea. But anyway, so what it gives you, it changes the results. And the expression that you get for this, for the mass of the active, is just the Yukawa. Sorry, this is the Higgs web squared. Okay, and this mass comes out to be like the tower of a star starts at phi squared over n5. Okay? Look at this formula. Can you tell me what happens if the web of the Higgs is equal to the web of phi? If the web of the Higgs is equal to the web of phi, I do get the mass of the active is lambda to the 1/4. The thing that I wanted to explain. Okay? It's not that crazy to come up with models or reasons why the two waves might be equal. For instance, if you write a general quartic, the most general renormalizable interaction between the bulk scalar phi and the Higgs field restricted to the standard model brane, is gonna, and you impose that this thing has a minimum, has a minimum for the potential, then H and phi are gonna be comparable on the minimum. That's just true for the general scalar potential. So the scale of, sorry, you're not, it's just I didn't say it, I should have said. So the M5 is the 5-dimensional Planck scale, okay? And it's fixed by 4-dimensional Planck scale in the sense of the extra dimension. So M5 is 10 to the 10 GeV.
The size of the dimension.
Yeah. It's related to the size of the dimension and 4-dimensional Planck, yes. So it's 10 to the 10 GeV. And, well, you know, have enough things to plug in numbers, okay? So what you get is that the mass of B minus L, once you plug numbers, is something like 170 GeV. This comes out for this, and by imposing that these two fields are equal, times the square root of this coupling alpha. So its coupling is 10 to the minus 10. And now this is okay with all constraints, okay? It's a heavy guy. The only thing that could see it maybe is LHC bounds, but the coupling is very small. So then it's okay. Right? And then you have the mass of this guy comes up to be lambda to the 1/4. So it's along milli-electron volts. So you get the right mass scale. And there's a whole tower of sterile neutrinos, which might be an interesting opportunity to test the model, where the mass is between 1 and 10 keV. Okay? So that's the start of the tower. Then, as we were saying, there's like a whole tower goes on. Okay, so a lot of those guys, but they're very heavy. And so to finish, so this is a scenario, you know, this is just like some little addition to the dark dimension. We just add this bulk B minus L gauge field. And then just imposing anomaly cancellation, we get naturally there's 3 neutrinos. We explain where they're massless. And we also get a very nice value for the mass of the active neutrinos under the assumption that the interactions that set the web of H and the web of phi are the same. Okay. This is actually a model, you know, it evades current bounds, but it's not too far from checking them either, because there's also Kaluza-Klein modes for the B minus L. Those will also appear in the LHC. And also the scalar phi and H can interact directly. So all of these provide opportunities for detection. And finally, since this connection is just general, happens no matter, it doesn't, once you fix this to be the same, doesn't depend on any other parameters of the model. And we're hearing yesterday in George's talk that in dark dimension you can take the vacuum area to be time dependent. This will also mean there's time dependent neutrino masses, which is an interesting signature as well. And so with that, I thank you for your attention and I finish.